Hello and welcome back to PC Retro Programmer. In today's video I'm going to be taking a look at the Tandy graphics adapter and in particular the three graphics modes that it offers you over and above CGA. So two of them are 16 color modes. There's one at low resolution, 160 by 200, and it's a genuine graphics mode, not a hacked up text mode like we have on CGA. And then there's a medium resolution mode, also at 16 colors. So these are modes 8 and 9 in the BIOS. And mode 10 is a high resolution mode, 640 by 200, but it's only 4 colors. So getting into these modes is really trivial. You just use the BIOS interrupt 10H set mode function and then obviously pass in 8, 9 or 10. So this is just like we do to get into mode 4 in CGA, very straightforward. Now the main difference is that in modes 9 and 10 there are 4 banks of 8 kilobytes instead of the 2 banks of 8 kilobytes that we have on CGA. In mode 8 there is just 2 banks of 8 kilobytes. But there's also some differences in the way the pixels are laid out. So modes 8 and 9 are pretty logical. You have 2 pixels per byte, so you have a high nibble and a low nibble. The high nibble is the first pixel and the low nibble is the second pixel. So this makes complete sense, of course. There's no bit planes or anything here. It's very, very straightforward, just like CGA, except 4 bits per pixel. The other mode, mode 10, is a little bit more complicated. I haven't quite worked out the details yet, but the manual seems to suggest that they have an even odd byte arrangement. And so each color, of course, takes 2 bits. One of the bits comes from one of the bytes, and one of the bits comes from the other byte. That's what I think is going on, but I haven't tried it out at this point. So obviously the pick of the bunch for us is the 320 by 200 mode, since it's the same resolution as the CGA graphics mode, except it's 16 colors. So this is straightforward, except for the 4 bank thing. So these can even be moved about in memory. There's 128 kilobytes of actually just ordinary RAM that you can select for the banks. And so you can actually have pages with this graphics adapter, which is again an improvement over CGA. At any rate, the first thing I thought I would do is just write a very small point drawing program for the 320 by 216 color mode, just to see how it differs from CGA. And I'm doing this mainly because on the main channel, PC Retro Tech, I'm reviewing the Tandy SX this month for Tandy. And I thought it would be nice to try and program the graphics adapter. So first of all, let me show you the little program that I came up with for doing dots on the Tandy adapter. So I called this Tandy ASM. And again, it'll be just like the CGA program that we had for this. But I'm just going to make the appropriate changes for this 320 by 216 color mode. This code actually started off life as a CGA point drawing function on the channel, and all I'm doing is modifying it for TGA. So it'll still take the X and Y coordinates of the point you want to draw and the color that you want it to be, but now of course the color will be 0 through 15 instead of 0 through 3 since it's a 16 color mode. The video memory is still addressable at the same location. It's segment B800 in the memory map, and so we don't need to change this piece of code. Of course, it's now a 32K block of memory instead of a 16K block, but that doesn't change its segment address. The first changes that we need to make are for the offset computation. So the two main differences are that there are now 4 banks of 8K instead of 2 banks of 8K, and we have 2 pixels per byte instead of 4 pixels per byte. So those both will change the computation of the offset. Now in CGA it was pretty straightforward. If you had an odd line, all of the odd lines were in the second bank, and so all you needed to do was just add 8192 to the offset if it was an odd line. In TGA things are a little bit different. There are 4 8K banks, And the way it works is that all of the lines on the screen that are divisible by 4, so 0, 4, 8, 12 and so on, they're all in the first bank, bank 0. Then all of the lines that are 1 plus a multiple of 4, so lines 1, 5, 9, 13 and so on, they're all in the second bank, bank 1. Then all of the lines that are 2 mod 4 are in the third bank, bank 2, and all of the lines that are 3 mod 4 are in the fourth bank, bank 3. So the computation now is actually 8192, 8 kilobytes, times the bank number. Now we're actually going to use a little trick that we used in the CGA case. Instead of computing the offset itself, it turns out to be cheaper to compute a multiple of the offset. And then at the very end, just divide through by that extra factor to get the actual offset. So in TGA, it's cheaper to compute 2 times the offset all the way through, and then at the very last line, just divide that value through by 2 again to get back to the actual offset. And that can just be done with a single shift by 1 bit at the very end. So all the values that we're going to compute here, we're going to be multiplying by this additional factor of 2, just for efficiency reasons. So it's really 2 times 8192 times the bank that we need to compute here. Now the bank number is easy, it's just the y-coordinate mod 4, and in binary it's easy to take things mod 4, it's just the bottom 2 bits. So this computation, 2 times 8192 times the bank number, is just taking those bottom 2 bits and moving them into the top 2 bits of the register. So we can actually do that really cheaply with 2 single bit rotates of the register to the right. So that'll take the bottom 2 bits, this bank number, and put them in the top 2 bits of the register, which is precisely the value that we want. The only problem is that it also has the rest of the y-coordinate still in there. Effectively, that's still in there divided by 4 now, since we did 2 right shifts of that value. So basically, we have the value we're interested in plus y divided by 4. And so we need to get rid of that extra y on 4. Now, one way we could do that is actually just to zero it out. And fortunately, the y on 4 part is entirely in the AL register. Y is some value from 0 to 199, and when we divide it by 4, we certainly have a value that fits easily in AL. So one way we could zero out that y on 4 is just to zero out the AL register. The thing is, we actually need the value y on 4 for the next part of the computation, so let's not throw it away. So first of all, let's put the value that we've computed so far, the value that we're interested in plus this y on 4, let's put it into DI, and then let's subtract the y on 4 away from it without throwing it away. So how do we get y on 4? Well, we just zero the AH register. Obviously y on 4 is in AL entirely, so if we just zero out AH, then what we're left with is precisely y on 4. So that's the value we need for the next step, so let's not throw it away, but we just subtract it from the offset. And now the offset is exactly the value we want, not the value we want plus y on 4. So a little bit of dancing around there, but we get there in the end. And so now the offset is the offset of the bank, multiplied by 2 of course, and we have y on 4 in the AX register. So the next thing we need to compute is the offset within the bank of the line that we have. This is obviously y on 4, and we need to compute its offset within the bank. And so each scan line takes 160 bytes within the bank. The reason for that is you have 320 pixels across the screen, and there are now 2 pixels per byte. So each scan line must be 160 bytes. So it's y on 4 times 160. That's the offset within the bank. So we need to add that to our offset. And of course, everything multiplied by 2 as usual. Now the code we use for this, all it's doing is just multiplying that value we've already computed, 114, by 320. And we actually had code in the CGA case for multiplying by 320. It's just this code here. So this doesn't actually need to change, interestingly enough. So the final part of the offset to compute is to do with the x coordinate. And remember, there are now 2 pixels per byte here. So the value we need to add to the offset is x divided by 2. But remember, we're multiplying everything through by 2, and so really we just need to add x to the offset. So that's trivial. And finally, now that we have the entire offset multiplied by 2, we need to divide it by 2 to get the actual offset. And as I explained earlier, that's just a single shift right by 1 bit. So now DI contains the offset of our point within video memory. There's a lot of computation there to get it, but it's not worse than CGA. In fact, I think it might even be slightly better. Now, the final thing that we need to do is compute a color and mask byte, and for that we're going to need which pixel within the byte we're dealing with. There's only 2 possibilities here. Either we're dealing with the left pixel or the right pixel. So basically, if the x coordinate is 0 mod 2, then we're dealing with the left pixel, and if the value is 1 mod 2, we're dealing with the right pixel. So fortunately, we actually can figure out whether we had a pixel that was 0 or 1 mod 2 because we added x to the offset here, and the offset was even. And so basically this DI value is exactly the same mod 2 as x. So when we do this shift right by 1 bit, what happens is that final bit gets shifted into the carry flag. So in other words, the carry is now x mod 2. And so we don't actually need to do any computations to get x mod 2. We already have it. It's in the carry flag. So basically we use the carry flag to figure out our color and mask bytes. Now I want to deal with the color and mask bytes differently with TGA than CGA. And the reason for that is in the CGA case, to move by 1 pixel to the left or right, we had to rotate our color and mask bytes by just 2 bits. But here, we'd actually need to be rotating by 4 bits because there are 4 bits per pixel. And this would get really expensive. There'd be 4 shifts for each of the mask and color bytes, which would be 8 assembly instructions, which is really just way too much. So what we're going to do instead is we're going to set the mask byte up so that 4 of the bits are zeros and 4 of the bits are ones. And then in order to shift left or right by 1 pixel, all we need to do is complement our mask byte. In other words, make all the zeros ones and all the ones zeros. And that can be done really efficiently in assembly language just by using the not instruction. That's exactly what it does. It just complements all the bits. So that's how we're going to deal with our mask. And the color itself, what I'm going to do is put the color information in the low half of the color byte and also in the high half of the color byte, and then use the mask byte to select the 4 bits we're interested in. So this is how we're going to deal with things instead of using rotates that we did in CGA. So this is what the code looks like. The first thing that we do is set up our mask byte. Now at this point we have a 1 in our carry flag if x was 1 mod 2. So that in that case we actually are interested in the bottom 4 bits of the byte. And so the way I'm going to set my mask byte up initially is that those 4 bits will be 0 and the high 4 bits will be 1s in that case. So let's see how we do that. So the carry flag is a 1 in this case, and we basically set all of the bits in BL to the same as the carry flag initially. So we'd have all ones in BL in this case. And then I just XOR the low 4 bits with ones so that they become zeros. So now we have 4 ones in the high 4 bits and 4 zeros in the low 4 bits. So that is the case where the carry flag was a 1. Of course, if it was a 0, we'd just end up with the opposite. We'd end up with 1s in the bottom 4 bits and zeros in the top 4 bits. So this takes care of our mask. Now the color information, as I said, I'm going to duplicate that in the low and the high half of the color byte. So we'll actually need to AND it with our mask, or actually it'll turn out we'll need to AND it with the complement of our mask in order to select the bits we're interested in. So let's duplicate the color information into both halves of our color byte, which is BH. So we just put the color in initially, that'll deal with the low 4 bits, and then we just duplicate it by shifting left by 4 bits and adding that back into the color byte. So now we can select the color that we're interested in the correct 4 bits just by ANDing with our mask, or as I said, it'll end up being the complement of our mask. So we're actually now set up. Our color and mask bytes are done, and let's see how the pixel drawing actually works. So first of all, we copy our color and mask bytes into the AX register. We don't want to mess them up, so we need to make a copy here. And so the mask is now in AL, and what it has is zeros in the bits that we're interested in. So basically, if we AND the byte that's currently in video memory with this mask value, then it's going to zero out the bits that we're interested in, basically clear them out, whatever they were previously. Then we complement our mask byte. So this is just using the NOT instruction in assembly language, just turns all the zeros to ones and ones to zeros. So now it has the 4 bits selected that we're interested in, and so we AND that with our color byte so that we have our color in the correct 4 bits, and then we just OR that selected color with our graphic byte and put it back into graphics memory. So it's really pretty straightforward. We just used the mask twice. Once to zero out the bits we're interested in, then we complement it to select the bits we're interested in of the color byte and combine the two together and copy out to video memory. So a very straightforward process. And that's actually all there is to our pixel drawing function. So the only thing that really remains is to write a little driver program which actually calls this function. And so I've used something very similar to the CGA case. Instead of drawing one diagonal line here, I'm actually going to draw 15, one in each of the TGA colors except color 0. There's not really much point in drawing a black line on a black screen, so we don't actually do that. So the first thing we do is to go into the TGA mode 9, and it's the same as going into CGA mode 4, except I use 9 instead of 4. And as I said, we're going to draw 15 lines, so there's a loop count of 15 here, which gets decremented down to 0 and stops. And the inner loop here is pretty much the same as what I had for drawing a diagonal line in the CGA case. You just use the same coordinate for the X and Y coordinates, so it's diagonal, and we just iterate from 199 down to 0. The only difference is I don't want all of these lines to be overlapping one another, I want them next to one another. So I have to shift the X coordinate by this dx value so that they'll end up next to one another. So here you can see I just add that dx value to the X coordinate before pushing it onto the stack for the function call. And then in order not to mess up SI, I just subtract it straight back off again so it doesn't affect the SI value that we're iterating. The only other difference is, of course, I want all the lines in different colors, and so I actually use the DX value for the color. Now, it's only a byte to specify the color, but you remember that you have to push a 16-bit register, so we just push the whole of DX here and we're done. So those are the only changes. Here's the end of the adder loop here. Once it gets to 0, it will stop, so it won't draw that line in color 0. And the remainder is exactly as what we had before: wait for key press, restore video mode, and exit to DOS. So let's actually save this and assemble it and run it on an actual Tandy and see exactly what this looks like on the screen. So I'm just going to copy this over to a genuine machine now, and we'll take a look at the results. Well, here goes, and I'm not expecting this to be much to look at, of course. And what I see with my eyes looks like 4 bands of high intensity CGA cyan, magenta, white palette, and then 4 bands in the low intensity of the same palette. Of course, if you look really closely, you can actually see that there are yellow and green lines and so on. All the colors are there, it's just an illusion because they're not very wide. But at any rate, it looks like we have the principles of operation worked out here, and we're off to the races. So we should be able to do some TGA graphics programming.